Well, welcome back. Thanks for joining me for part 2 of this video lesson about a chi-squared goodness of fit test. In the first part of this video, we were talking about Malcolm Gladwell's claim about NHL players' birth months. And we wrote the hypotheses, calculated expected counts, and then calculated a chi-squared test statistic. So let's go to page 2, talking about the conditions that need to be met for that test statistic to follow a chi-squared distribution. So let's take a look. There are 3 conditions that should be met. So the 3 conditions are random sample or random assignment. So we have a random condition. This was met in this case. We had, or Malcolm had, we have a random sample of 80 NHL players. The next condition is that all expected counts, not the observed counts, but the expected counts. All the expected counts are greater than 5 is the next condition. For the test statistic to follow a chi-squared distribution, this is the particular condition that needs to be met. So the expected counts we had on the previous page, they were all 20. So all of the expected counts are greater than 5. All were 20, which was greater than or equal to 5. So that condition is met. And then the observations can be considered independent. We typically use the 10% condition when we have a random sample, sampling without replacement. So I'm not too sure about the NHL, but we'll assume there are more than 10 times the sample size. So that would be 800 NHL players to sample, or in the population. I'm not sure if that's a good assumption, but that's the assumption we'd need to make. Now you'll notice in these conditions we have a random condition, the expected counts or the large counts condition, and then independent. You'll notice something's missing. What condition is missing that we normally check? Well, the normal condition is not present. Why is that? Because a chi-squared test statistic doesn't follow a normal curve. Our p-hat distribution that we used before follows a normal curve. Our x-bar distribution follows a normal curve. Our difference in p-hats follows a normal curve. Our difference in x-bars follow a normal curve. But this chi-squared distribution, or this chi-squared test statistic, doesn't follow a normal curve. It follows a chi-squared distribution, which we have a picture right below here. You can see that on your screen. The chi-squared distribution, there are different distributions for chi-squared, and they're based on the degrees of freedom. So we said the degrees of freedom in this case was 3. Degrees of freedom was 4 minus 1. So we want a chi-squared distribution with 3 degrees of freedom. Chi-squared distribution is a right-skewed distribution. You can see here it's definitely not normal looking. It is not symmetric. It is unimodal, but it is not symmetric. So let's calculate the p-value in 2 ways. One way is with Table C. Table C is provided on the AP exam, and it's also in the back of your textbook, very, 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 very far in the back of the textbook, Table C. Table A is for normal curves, Table B is for t-distributions, and Table C is for chi-squared distributions. And this is our last table that I get to introduce you to. We don't typically use the table, but I thought it might be helpful to check out how you'd use the table. So notice by the picture, the chi-square value is this boundary, and the probability, the p-value, is always to the right of the chi-squared. So the chi-squared is always the lower bound, and the upper bound is always going to be some large number like infinity. So to use the table, we're going to find on the right side, we'll find our degrees of freedom, which is 3. And then we're going to, let me highlight that. We're going to go across this row for degrees of freedom 3. And we look inside with those numbers and find what number's closest to our test statistic. Our test statistic was chi-squared equals 11.2. So we find, it looks like 11.2 is between these 2. And it's pretty close to the one on the right. But then to get the p-value, it's an estimate. It's a range of possible p-values. So our p-value is somewhere between 0.02 and 0.01. So we would say the p-value is between 0.01, and 0.02. That's using the table. We could also use the calculator function. Now, typically when we want to find an area with our calculator, we would use a CDF function. So if you want the p-value, you'd be using a CDF function. We are not going to use normal CDF because it's not a normal curve. You're not going to use TCDF because it's not a T distribution. You're going to go to second vars and you're going to scroll down until on my calculator it's number 8. And that says on my calculator chi, a cursive looking X, CDF. That's the function that you'll use on your calculator. So if you select that, if you have a TI-84, it will say lower, upper, and then DF. And that's similar to the TCDF command. You have lower, upper degrees of freedom. The TI-83, you'd have to separate those by commas. So our lower bound is our test statistic. That's always going to be the case with these. That would be 11.2. The upper bound is some large number infinity. The degrees of freedom we said was 3. And we get a p-value of 0.0107. Notice this p-value is between what we said it would be between. It's between 2% and 1%. So this is a more precise way to get the p-value using the calculator function. So what conclusion would we make? Well, it depends on our alpha level. If we use the typical alpha level of 5%, I encourage you to pause the video, see if you can conclude the significance test the same way we've concluded all the previous significance tests. So we have our explicit comparison. Our p-value is less than our alpha level. We have a statement about the null hypothesis. We're rejecting the null. And we mentioned that we have convincing evidence. It's not proof. We could have made a type 1 or type 2 error. It's evidence that the distribution of NHL player birth months are not uniformly distributed. Now, typically in statistics, if you end up rejecting the null, you would do something called follow-up analysis. You would only do this on the AP exam if you were asked to do follow-up analysis. You don't have to include it. But follow-up analysis would ask the question, we got a test statistic of 11.2. That was very far away from what we'd expect if the distribution was uniformly distributed. So we would go back to our contributions, or our components they're also called, and we'd see which one made the biggest contribution. And it looks like the biggest contribution was that first quarter. Now the contribution doesn't tell you if that's more or less than you expected, so you'd actually have to see. We observed 32 and we expected 20. So the first quarter made the biggest contribution. We had more than we expected. We had 32 rather than. But that is a chi-squared goodness of fit test. Basically the 4-step process that we've kind of strung out. Now there is a way to calculate the test statistic and the p-value with your test shortcut. Now the TI-83 does not have this shortcut, but if you'd like it, I have a program, or I could just let you borrow a TI-84. So if we go to the stat, and then over to tests, stat, and then over to tests, if you hit the up arrow, you'll get to it fastest. There's a test called chi-squared GOF test. The GOF stands for goodness of fit. We'd like to know how good, it should be called wellness of fit, I think, how good the sample data fits the claimed distribution. So to do that, if you click on that, you'll be asked for observed, expected, and then the degrees of freedom. Well, I already know the degrees of freedom. The observed says L1 and the expected says L2. So you're going to have to go to stat and then edit. And this is your list menu, and you're going to need to put your observed counts in list 1 and your expected counts in list 2. So I know all the expected counts. I remember those. Those are all 20. So you type 20. Make sure nothing's below 20. Those are the expected counts. The observed counts are 32, 20, 16, and 12. So after you've typed those into list 1 and list 2, you'll run this chi-squared goodness of fit test. The lists are already prepared. It's 3 degrees of freedom. and when you hit calculate, it will calculate for you. It will tell you the chi-squared is 11.2 and the p-value is 0.0107 with degrees of freedom 3. It also tells you the contributions. So if you scroll to the right, you'll see these values. So those are the contributions for quarter 1, quarter 2, quarter 3, and quarter 4. So our chi-squared test statistic formula, chi-squared equaled, we did the observed minus the expected squared divided by the expected, and we did that for each category, and then we found a sum of all those. So that's the formula for a chi-squared goodness of fit test, and that formula is provided on the formula sheet. And I'll end this video with a couple fun facts about chi-squared distributions. Chi-squared distributions are only positive values. Nothing goes to the left of 0. There's no negatives. And it is a right-skewed distribution. It's defined by degrees of freedom. And as the degrees of freedom increase, the distribution becomes less skewed. So you can kind of see here that if you only have 1 degree of freedom, it's this line for the chi-squared distribution. But if you have 8 degrees of freedom, notice it's less right skewed. So actually there's a limit here is what it's called. As the degrees of freedom approaches infinity, the shape of the graph becomes more and more roughly normal. The mean of a particular chi-squared distribution is the degrees of freedom. So that's kind of interesting, fun fact. As a right skewed distribution, the mean is greater than the median. The variance of the distribution is 2 times the degrees of freedom. That means the standard deviation would be the square root of 2 times the degrees of freedom. That's just fun fact, not really required for the AP exam. If the degrees of freedom is greater than 2, the mode or the peak of the distribution is 2 less than the degrees of freedom. So for example, if the degrees of freedom is 8, which is the blue graph here, it has a mean of 8. And the mode is at 6. So there's the mode at 6, and the mean would be right here at 8. Those are just a couple facts about chi-squared distributions. Those are not as important as the other details that we've had in this lesson. Well, thank you for watching these 2 videos. We were able to fit it in 2 videos, not 3. So look forward to working with you this week about more practice with chi-squared test. This particular goodness of fit test, and there's a couple other chi-squared tests that we'll learn about. Thanks for watching this video. See you later.